Welcome back. We're going to be doing an example of titration analysis here. This is showing us the data obtained from doing 4 trials of an acid-base titration. And let's just read through this to understand what the chemical reaction is. So a lab group decides to test a manufacturer's claim that an antacid product contains 200 milligrams of sodium bicarbonate. Each tablet was placed into an Erlenmeyer flask, 10 mils of water was added, and then the tablets were crushed. An indicator was added to each flask, and then each sample was titrated with 0.200 mole per liter hydrochloric acid. The titration evidence was collected in the following table, blah, 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 blah. And the question is, what is the mass of sodium bicarbonate in the tablet? So we want to know how much sodium bicarbonate is actually in the tablet. On the label for the product, there might claims that there's 200 milligrams, and we're actually testing it. And this is something that you can do with titrations. Here at the school, every second year or so, we'll do one where we test how much vitamin C is in orange juice, and we actually try to determine if it's accurate, if the label's accurate. So, all right, let's dive in. So, from our previous video, and hopefully you watched that one, the titration setup looks like a burette with a flask. And this write-up says that we had a tablet placed into an Erlenmeyer flask, and there's 10 mils of water, and the tablets were crushed. So we can assume that the tablets were completely dissolved, so all the sodium bicarbonate is dissolved, and there were 10.00 mils of it in that flask. And in the burette, we're going to start with a certain amount of titrant, and in this case I think it's hydrochloric acid. So the hydrochloric acid is going to get poured into the burette. And with each trial, we're going to record its initial burette reading and its final burette reading. And over the course of the titration, we're going to add some of this base, and this hydrochloric acid. It'll be added to the analyte inside the flask, so the volume will drop a little bit. And we record the final volume when we get to the end point. And the end point is when the pH indicator changes color. Now, there's something we need to watch out for here, and that's the first trial. You notice in the first trial it says the color is dark pink. And it looks like, the write-up doesn't say this, but it looks like the pH indicator here is phenolphthalein. And phenolphthalein, when you use it in a titration, you really want to aim for a light pink color. Dark pink tells us that we overshot it. So the dark pink there, we're not going to include this data in here, but it's recorded anyway because it kind of gives us an approximate, for whoever was performing this titration, it gives them an approximate range, like a volume that they need to add until they start getting close to the end point. But because it says dark pink, that tells me that it's a little bit of an overshoot. Nevertheless, I'm going to calculate how much volume of hydrochloric acid was added, and that was 11.0. So the first time through, you add 11.0 mils of hydrochloric acid, and your pH indicator goes dark pink. So that tells me it's an overshoot. Maybe we added too much acid. So it's around 11. You go back, you set everything back up again. You crush another tablet, put it in there, mix it with 10 mils of water, and you do trial 2. And in trial 2, the volume that we add is going to be just the difference between these two numbers. So 21.7 minus 11.6. And I get 10.1. So you can see it's a little bit smaller than 11. Initially, when we add 11, we go too far. It's dark pink. Second trial, we slow it down. 10.1, it's light pink. So that means we hit it, we hit the proper value there. Okay, let's try it out with trial 3, and it's usually pretty common to do multiple trials here. So 31.7 minus 21.7, we get 10.0, and we'll do the last one, 41.8 minus 31.7, and I get 10.1. All right, so now let's determine the mass of the sodium bicarbonate in the tablet. So first thing I should do is write out a balanced chemical equation. And the nice thing about acid-base titrations is that most of the time they're one-to-one relationships, one-to-one mole ratios. So in this case, we would make NaCl and water. This one's a little bit of a weird one. I'm not expecting you to know this one, but this is, HCO3 will form up with the H, which makes carbonic acid, which makes the H2O, and it makes CO2. Okay. Anyway, we're trying to neutralize the sodium bicarbonate with the hydrochloric acid, and we can determine the volume of hydrochloric acid by taking the average that we get from the 3 trials. So I can take 10.1 plus 10.0 plus 10.1, and I divide it by the number of trials I did to get those numbers. So I got 3 trials, and that gives me an average volume, 10.1 plus 10.0 plus 10.1 divided by 3 gives me an average volume of 10.06 repeating, which will just, I'll keep that number, 10.06 repeating mils. But we're going to worry about sig digs a little bit later on, but that's just, we'll keep that as a reference for now. All right, now let's turn back to our problem. Remember, the titrant, the thing in the burette, is usually the thing for which you know the volume and its concentration. And we're told its concentration here. It's 0.200 moles per liter. All right, so with its concentration, and we take the volume and convert it into liters, we can take the concentration and the volume and determine the number of moles of the acid. So number of moles of hydrochloric acid will be those 2 numbers multiplied by each other. So take that average volume and multiply it by 0.200, and we get 2.013 repeating moles. So that's how many moles I have of the hydrochloric acid. And since it's a 1-to-1 ratio, I can then say the number of moles of sodium bicarbonate, because we're at the end point, okay, we hit the end point for each of these 3 trials, we got the volumes, we knew we can then, and this is a 1-to-1 ratio, we can say, well, however many moles of hydrochloric acid there are, there must have been the same amount of moles of sodium bicarbonate inside the analyte. Inside the 10 milliliter sample we had, we must have had the same number of moles. So that would be 2.013 moles. So what we just determined here with this number is how many moles of sodium bicarbonate were in this 10 milliliter sample at the start of our titration. And when we added all that acid, we added 2.013 moles of acid, which completely neutralized the 2.013 moles of sodium bicarbonate in the sample. And that's why when you hit the end point here, that's why it should give off the light pink color telling you it's been a neutralized solution. You completely neutralized the sodium bicarbonate, because it's acting like the base in this case. So we use the mole ratio here then to determine the number of moles of sodium bicarbonate. Now all I have to do is convert that into mass. So I got to figure out the mass of sodium bicarbonate. So this one's a little bit different in that we're not determining the concentration of sodium bicarbonate. I can actually, once I have the moles, I can just jump straight towards the mass. And to do that, I need to multiply by its molar mass. And the molar mass of sodium bicarbonate is 22.99 plus 1.01 plus 12.01 plus 48. 84.01 grams per mole. Okay, so I'm going to multiply by that number, and so let's just run through our numbers again. I want to make sure I get them all down accurately. And divide by 1,000 times 0.200. Oh man, way off. Oh my gosh, made such a big boo-boo. All right, I figured I probably made a mistake. I was not paying attention. Okay, so this, make sure this is 0.002013. Oh my gosh. Anyway, not a big flub. All right, so that just changes that number. Should be a little bit smaller, 0.002013, 0.002013 moles of sodium bicarbonate, and then we multiply by 84.01, and I get 0.169 grams. Here's the weird thing, 0.169 grams, and if I convert this into milligrams, I would get 169 milligrams, because a milligram is 1,000th of a gram. All right, so we got 169 milligrams of sodium bicarbonate in each tablet, and the manufacturer said there's supposed to be 200. You got gypped. They're lying to us. They owe us another 31 milligrams of sodium bicarbonate. What the heck? All right, so that's a sample titration calculation. The only thing that's a little bit different with other titration calculations is sometimes you don't multiply by the molar mass just to get the mass right at the end. You might find these number of moles, and you would divide it by the volume here, which is the 10 mils. Or convert it to liters first, and then you would find your concentration. Okay, that's another common thing you can do right at the end here, but there you go. There's the titration. Usually a source of confusion for a lot of students, even when they get it into grade 12. We do multiple titrations in grade 12, and we learn about a different type of titration other than acid-base. But anyway, thanks for watching this video. As always, let me know if it wasn't clear or if I need to explain something again. I am going to do another video on titrations, kind of showing, you know, showing the pH change over the course of an acid-base titration. Yeah, and then that's it. All right, see you in the next video. Bye.